Trusses are a particular example of systems of rigid bodies, and they have a couple of requirements. Number one is that they consist of a system of two force members, so every rigid body in the system is a two force member, that all the connections between the rigid bodies are frictionless pins, and lastly, any applied forces to the truss are only applied at the pins, or sometimes known as nodes or joints. Okay, so a very simple example is shown here. I have a two-bar truss. It's supported at 2 points, and it has an applied load P at one of the nodes of the truss. And a classical example in such a problem would be, say, to find the forces in the bars. So the way one can go about doing this is to draw a free body diagram. And if I draw a free body diagram and note that the forces in the two bars have to line up along the line of the bar, because each truss bar is a two-force member. I have the picture shown here with FA and FB as the bar forces, and if I now apply equilibrium to this picture here, I find out the bar force in A is √2 times P, and the bar force in B is minus P. So this is a very simple example. Now, if we want to ensure that the entire truss is in equilibrium, we have to be a little bit more careful, because when you have a system of rigid bodies, it's not just that you have overall equilibrium of the system, but that each body of the system is individually in equilibrium. So if I separate out all the parts of my truss here, then I have two bars, the slanted one with the force FA and the horizontal bar with the force FB, and then I have the pin that has also reactions FA and FB acting on it and the downward force P. You'll notice that because of the way I've drawn my pictures, which have taken advantage of the fact that the bars are two force members, I've ensured that I have equilibrium of each bar. Okay, and the only thing that I have to ensure is that I have equilibrium of the pin now. And so I can do some of the forces in the X and the Y directions at the pin, and indeed I see that I get FA is equal to the square root of 2P, and that FB is equal to minus P. So it's consistent with what I had before, and everything is in equilibrium now. Let's look at a slightly more complicated example. So here I have a truss with joints at A, B, C, D, and E, and there's a force located at joint E, and I have truss bars connecting them as shown. Now, if I want to analyze this system, say to determine the bar forces, what I need to do is use equilibrium on each of the bars in the system and each of the pins in the system. So there are 5 pins, and then there's 1, 2, 3, 4, 5, 6 bars in the system. Okay, one would start with a free body diagram where one isolates each pin and each bar individually, and you'll notice that I've drawn all the forces to line up parallel to the bars, because I'm going to take advantage of the fact that I know that each bar is a two-force member. So taking advantage of the fact that each bar is a two-force member, that allows me to really reduce the number of unknowns in the problem. So if we start, I'll just start labeling them. We have the reaction forces from the pin support at A, so I'll call those AY and AX. I also have BX and BY. Those are the support forces from the support at B. And I also have CY and CX. So those are all unknowns in my system. And now I also have my bar forces. So over here I'm going to call this F1, and these are equal and opposite right here. And these two guys up here are also F1, just simply by action equals reaction and taking advantage of the fact that this bar here is a two-force member. Okay, so that really reduces the number of unknowns. Originally in that picture it looked like there was 1, 2, 3, 4 unknowns, but really they're just one unknown. And the same holds down here. I have F2, and these two forces are also F2. These two forces I'll call F3, and that makes these two also F3. Let's call these two F4, and that will make these two F4. Let's say F5, F5, F6, F6. Okay, So if we look at this, there are 6 bar forces, one for each bar, and I also have 6 support reactions. So there are a total of 12 unknowns. And the equations that are available to me to solve for these 12 unknowns are the equilibrium equations. And those are the equilibrium equations, one set of equilibrium equations for each rigid body. Now I've already used up the equilibrium equations for each bar, and the only equilibrium equations available to me are the equilibrium equations for each joint or node. And the joints and nodes are subjected to concurrent forces, so there are only 2 equilibrium equations there. So I have 5 nodes, and I'm going to have 2 equilibrium equations, so that's going to give me 10 equations in this setup here. So if I look at this, actually 6 plus 6 is not equal to 16. 6 plus 6 is equal to 12. So I have 12 unknowns and I have 10 equations available to me, so 10 equations of equilibrium. So I'm short 2 equations here. So this system here is statically indeterminate of degree 2. Systems that are statically indeterminate cannot be fully solved. Let's go ahead and look at yet another example here. So here I have a truss. It's composed of 1, 2, 3, 4, 5, 6, 7 truss bars, and it's supported at point A with a pin, and it's supported at point B with a roller, and it's subjected to a force P. If I draw the free body diagram for this system and I take into account the fact that all the truss bars are 2 force members, so I won't even draw them in, I'm already going to use the fact that they're in equilibrium, I have the picture as shown here. So I have each node drawn in, and I have the forces acting on each node in the orientation in which they act. So at node A I have the 2 support reactions AX, AY, and then I have the bar forces from bar 1 and from bar 2. So if we'll go ahead and call this one over here bar 1, and we'll call this one over here bar 2, so that gives me the bar force in 1 and the bar force in 2. So I've used the symbol R here for the forces in the bars. And I can go through for all the other bars. I have the forces in bar 3, bar 4, so 3, 4, 5, 5, 6, 6, 7, 7. So this is my setup here, and I can go ahead and count my equations. There are 3 support reactions, so AX, AY, and BY, and there's 7 bar forces. So there's a total of 10 unknowns in this system. It has 5 nodes, and each node is subjected to a set of concurrent forces, so there's 2 equilibrium equations. So that gives me a total of 10 equilibrium equations. So I have the same number of equilibrium equations, 10, as I have of unknowns. So this system is statically determinate, and so we can actually solve this truss system for all the forces in the bars and all the actions on the pins. That would allow us to design the system, say pick the sizes of the members and things of that nature. Now there are a couple of ways of doing this analysis. One is something known as the method of joints. This is probably the most classical method of solution, and in this method of solution you would typically find the support reactions AX, AY, and BY using overall equilibrium of the truss. So just draw the free body diagram of the truss as a single entity, and then find AX and AY and BY, and then you would proceed node by node, or pin by pin, or joint by joint, depending on the terminology you want, through the truss, trying to determine R1 through R7. So in this particular case, we could, for example, we could start with moment equilibrium about A. So if I were to take the truss and look at the forces acting on it, if I do moment equilibrium of the truss in A, then that will tell me what BY is, for example. And from there I could do force equilibrium in the vertical direction and force equilibrium in the horizontal direction, and that would tell me what AX and AY were. So that's step one of sort of this classical method. And now I can start to work my way through the system. So for instance, if I look at the node where B is, I can use that set of forces, and I can do vertical equilibrium and horizontal equilibrium, and that would tell me what R6 and R7 are. And so now I've fully solved that node there. I could then, for instance, move over to node A if I wanted. I already know AX, or at this point I know AX and AY. So again, equilibrium in the vertical, equilibrium in the horizontal would tell me what R1 and R2 are. Knowing those two quantities, I can now, say, move off to the top left node. And at the top left node, I know what R1 is now, so that actually tells me what R3 is. Note that I know the orientation of all the forces. They always go in the direction of the bars, and I know the geometry of the system. So knowing R1, I can get R3 using equilibrium in the vertical direction. And then I can use horizontal equilibrium, and that will then tell me what R4 is. I could then move over to the top right node. At this point I know what R7 and R4 are, and I know what P is, that's applied force. So the top node then, just using equilibrium at the top node, that then tells me what R5 is. Okay, and at this point I now know all the bar forces. I could then go back to this bottom node and I could do force equilibrium of this node, and that could be a double check. So I can use that to check the consistency of my calculation. Okay, so this is the classical method. Typically you start with the support reactions, though you don't have to, but that's usually typical, and then you just move your way through the truss system, going joint by joint, trying to find joints that you can actually solve for the unknown forces that are acting at those joints. The other way to do this is just simply think of this as a linear algebra problem, and you just set up the sum of the forces in the x and the y direction at the 5 nodes. That'll give you 10 equations. There are 10 unknowns. It's going to be a linear system of equations, and you can just feed that 10 by 10 system into a computer and let it solve it for you. So that's another common way of dealing with truss problems. Let me mention one other technique. This is something known as the method of sections. And this is a technique that's usually quite useful if you only want a little bit of information. So suppose I have this truss as drawn here, and it's subjected to a force P, and my question is, I'd like to know the bar force, but just in one particular bar. Okay? So I'm not interested in knowing all the bar forces and joint forces, etc., but I just want to know the force in one bar. And the method of sections is just a clever use of free body diagrams to help you determine an unknown. So what I can do is I can make a section cut across part of the truss and draw a free body diagram. So I've drawn my free body diagram, and I've put into the picture the force that I'm interested in. That's F1 as I've labeled it. But because I've cut through 2 other bars, I've exposed the internal forces F2 and F3. The only thing that I'm interested in is F1. Well, if I look at my picture carefully, I see that the lines of actions of F2 and F3 pass through a single point, and I've labeled that A. That actually happens to be one of the nodes of the truss up over here. But now what I can do is I can do moment equilibrium in A, and because F2 and F3 pass through A, they will not appear in the expression for moment equilibrium in A. So I'll have F1 times L minus P times 3L, so that's the lever arm for P, from P all the way over to A, and that has to equal 0. So that allows me to determine the force in the bar that I was interested in. I find out that F1 is equal to 3P. So that's a fairly straightforward way of finding just limited information, and that's known as the method of sections, and it requires a bit of cleverness to be good at it. Okay, but the main remark here is that there's a basic operating principle at play, and that is that every part of a body needs to be in equilibrium. So the overall body has to be in equilibrium, half the body has to be in equilibrium. Any subset of the body that you pick needs to be in equilibrium for the entire system to be in equilibrium. And you can use that fact to allow you to determine a lot of unknown quantities about how a particular system behaves in practice.